Hello again, it's Joel Ross. So this video aims to answer the question, what is programming? And provide a little bit of context for what you're going to be learning in this course. So I'm going to do this more as a presentation, so we'll have slides and stuff. All right, so there's our question, is what is programming? Well, let's see. So we're the information school, and our motto here is that we make information work. So really what we're interested in is we're interested in working with information in some way. So this usually involves working with data of some kind. So what we want to be able to do is we want to take that data and be able to convert it and abstract it and sort of extract some information out of it in order to be able to gain some insights and actually do something useful. So let's talk about how we might do that with programming. So let's consider a specific example, some specific data that we might worry about. So this here is a picture of some data from emergency room visits that involved an injury from a consumer product. So if someone hurts themselves with a vacuum cleaner and has to go to the emergency room, they end up in this chart effectively. And this is a set of data that's from 2014. I'm sure it's been updated recently, but this is a fun data set that I've got. So this is some raw data, right? It's just a bunch of numbers, a bunch of information. You can kind of begin seeing a little about what this might look like. But so the question might be, what kinds of information would we like to be able to convert this data into, right? What questions might we ask? So take a minute, you can think about like what kinds of questions you might get out of this data. You can pause the video, think about it, discuss it with a friend if you have one nearby. All right, so while you've probably come up with something that might be a really interesting question, we can take as example a fairly simple question, because at least that's a working example that I can go with. So like maybe one of the most basic, like the first question you might have think about, and I said here's a list of emergency room visits from consumer products, is you might think, well, which product was the most dangerous, right? Which vacuum cleaner is most likely to hurt somebody? Because we want to know that so we can get that vacuum cleaner out of the market, or warn people, or fix something, or solve a problem in some way. So this is an example of what would be called a searching problem, right? We want to go through this list and I want to find a particular example. I want to say which vacuum cleaner is the most dangerous in some way. Great. So we have that question. This is good. And then what we now need to do is figure out how do we go about solving this question, right? What do we do? And don't say use Excel, because the whole point is figuring out how we could do this with, programming type stuff. So great. So how might you answer this question? So again, as a thought experiment, think about if I like printed out this report, right? And I have all this data and I had every single entry that, as a little scrap of paper that had ever been created on this. And I handed you all that boxes and boxes of paper. And I said, here's all the emergency room visits. Tell me which vacuum cleaner was the most dangerous. How would you go about doing that? What would you do? How would you solve that? Yeah, and so what you might be is you might say, okay, like maybe a really basic example is you might like say, well, let's count them all up, right? Let's take a tally. Maybe we'll take a list of all the products that we've got, and I'll just go down the list one by one, and we'll figure out which product had the most, and we'll just like put a little tally mark next to each one whenever we find a product that caught someone to the emergency room, and then in the end we can go through, once we've got them all listed together, we could say, let's go through now, like check all the tallies and go find which one has the most tallies, and whichever one that was the most dangerous vacuum cleaner, and we should like tell those people, let them know. Great, awesome, look, we've solved the problem. This is amazing, everything's fixed and perfect. Cool, so that would let us be able to solve this problem by hand, without any programming. We're all good to go, life is fine, I don't have to take this class, everything's good. Oh, there's the end of my question, which product was dangerous? So the question is, I'm not creating slides, so I do a lot of slide stuff. So the question is really like, should we do this by hand? Is that something that, given this tallying procedure we came up with, is that a good idea? And the answer is, of course, no, we don't want to do that by hand. That would be really not cool. We would not enjoy that, right? It'd be really slow, right? You have to count through all those things. I mean, look at how many items are in this list, right? There's 266,000 rows here, and I don't think I've even scrolled all the way down yet, right? This thing is huge data set. So this is going to be super slow. It's going to take forever. It's going to be tedious. It's going to be so boring. We do not want to have to do this. We don't want to deal with it at all. And it's going to be actually really error prone, right? It's really easy for you to make a mistake, right? Maybe you're going to you'll lose your spot, or you'll get distracted because it's slow and tedious, right? Maybe you'll miss your tallying mark. You have to go refill your pen. Something can go wrong, and in which case suddenly you've lost track of records and everything's falling apart. So this is probably not something we want to do by hand. There's other kinds of errors, problems might come across if we try doing this by hand, which you might not have thought about. There's a question about how we can scale this. So for example, this works great with our 266,000 products, But if we want to then say, well, this, yes, but that was just the US market, we would now want to consider an international market. We want to look at all products across the world, then like suddenly we now have to do that again, but now our tallying work becomes even bigger, and we have to basically do the same work, but we have to do it more so. It takes longer and slower, we don't want to deal with that. There's also the question of then how we might, I don't know if you can see this behind the, here, I'll show the slide entirely. Oh, I don't know if that's working. Okay. There's a question then, of course, how we might reproduce this work, right? If I want to be able to see it, if I want to be able to, like, so for example, if I go through my data and I figure out that the Acme vacuum cleaner is the most dangerous vacuum cleaner in the world, sends hundreds of thousands of people to the ER every year, I might go to the Acme and say, your vacuum cleaner kills people, and they're going to probably say, like, can you double check your numbers? Because that seems really inaccurate. And we'd want to be able to do that work again. I want to reproduce it, but I also don't want to have to sit down and retally every single number over and over again, right? That would not be cool. So we want to be able to have some kind of repeatability, but we're not quite sure how to get that to work. So great, so we have this process, right? I can count things up, I can tally them. That'll work, that will solve the problem. But we don't want to do it by hand, right? We want to find someone else to do that. I don't want to do it. I don't want you to do it. We need to find someone else, right? We need like an assistant, right? We need effectively like the world's greatest research assistant who will be able to basically be like, let's find someone else to do that boring work. Someone else who maybe, I don't know, won't get bored tallying numbers, who won't make mistakes, right? Who won't lose their place. And maybe someone who can actually do that kind of basic counting task really, really fast, way faster than we ever possibly could. That would be great, right? Is there anybody out there that might be able to meet this criteria? There is. We've got our new assistant, right? Our new assistant is a computer, right? That's basically what computers do. A computer is just going to be something that we can give a set of instructions to, and then, here, I'm going to put this back here so you can see my gesture. So a computer is going to be a set of people that we can give instructions to, and they're going to be able to then do that work for us without getting bored, without complaining much, without making mistakes, and with being able to just do this over and over again. I mean, the instructions we had to give were really pretty simple, right? We'd say go through everything, count them all up, and figure out which number is bigger. Anybody can do that. Like, the computer doesn't have to understand why it's doing that. It can just go ahead and say, like, whatever, I'm counting things, and I'm happy counting. That's great. Anybody can do this math. A computer can do this math. My 5-year-old could do this math. So really, the hard part here is just figuring out what instructions we want to give, and then telling the computer to go follow those through the instructions. Cool. Great. So really that's the answer to do is all we have to do in order to like solve our problem without having to get really bored ourselves is to be able to tell the computer to do this work. So this is great. We need to just tell the computer what to do and problem solved, and we know what dangerous vacuum cleaners are. Great. Cool. There's one problem with this issue though. Computers don't actually speak English, so I can't just say go through the numbers and the products and tally up the vacuum cleaners because the computer doesn't understand what that means. Computers don't speak English. They don't speak any natural language at all, actually, because they're not humans. So what we need to do is figure out how we can talk to the computer in order to explain to it what we want to do. And that process of talking to the computer is what we refer to as programming. In this case, we're going to give instructions to the computer to tell it what to do. So programming for us is going to be writing out the instructions for the computer in a language that it understands, in a way that it is able to speak, and hopefully a way that we can then write it so they can understand what it's doing. And that's really what programming is. So as a fun fact, because I always have to share this fun fact whenever I talk about programming, the first computer programmer to ever live was Ada Lovelace, who wrote the first computer program in the mid-19th century. Ada she wrote a basic computer program to explain how a machine called the analytical engine would be able to effectively compute what are called Bernoulli numbers, which are this mathematical sequence of numbers. It's kind of like prime numbers, though not a little bit different. But basically, she wrote down a series of steps that this machine would be able to go through in order to be able to calculate a number. It's steps that the machine would understand how to do and how to run, and that was the first computer program. The impressive part being is the fact that the computer didn't actually exist. This machine was a purely hypothetical idea where someone said, it'd be cool if a machine worked this way. And she said, yes, and if it worked that way, here's how you would give it instructions. So that's the big thing to do. The other fun part of this course, the story, is that Ada Lovelace is the daughter of the Romantic poet Lord Byron. And the story goes that she was raised by her mother to be a mathematician because her mother hated her father so much that she didn't want her daughter to become a poet. So she steered her into mathematics. Anyway, so our goal here is we need to be able to tell the computer that speaks the computer in a language they understand. Computers in modern computers in general speak a language called binary, which is a language that's going to be a series of zeros and ones. It's binary numbers. This roughly corresponds to whether or not an electric circuit has a charge running through it or not. Like 1 means yes, there's electric arc there. 0 means no, there's not. Really, really roughly. We're not doing hardware in this class. But the idea is that that's the language computers speak. So we could clearly write down instructions that look a little bit like this binary structure in the green box. And that would be able to tell it what to do. I have the English translation on the side, so you can be able to see what happens. Cool. So if we were able to write down a whole bunch of zeros and ones, that tells the computer what to do, and the computer could then do some stuff and make things happen. Good? No, this is not good, right? Because people don't read binary, right? Like you can't just look at the zeros and ones and be like, oh yes, clearly I understand what's going on and I speak zeros and ones fluently. No one does that. I hope no one does that. Maybe no one does that. So the idea is we want to figure out like, well, okay, I can't do that, zeros and ones, but this other stuff, this English you wrote to the side, like that kind of makes sense. Why can't I just do that? Can I just write down load contents of A and like let the computer be able to and like have some way of translating that into zeros and ones? And that's exactly what we do. That's the point. So what we're going to do is that we could write down sort of a version of that, right? We're going to sort of get rid of some of our principles. We'll sort of try to clean it up a little bit. And we could write down that series of instructions in something that looks kind of like English, right? We'd say, great, let's load A, B, C, multiply, subtract, add, store. Basically give it this set of instructions. And then what we'll do is we'll write those down and then go through and basically do a massive find replace to say like, well, everywhere you write the word load, let's replace that with the right sequence of 0, 1, 0, 1, 0, 1. So effectively doing sort of just like a one-to-one translation step. And we could do that for entire computer programs. That would get old and tedious, right? That's a lot of work, but it seems really simple. So really what we're going to do is we're actually going to use a computer program to go through and do the find replacing in order to be able to explain how to do other computer programs. So then that'll be our process. So we'll be able to write something that is at least generally human readable, right? Something that we as people can kind of understand. We're going to run that through a computer program, what's called an interpreter. And the interpreter is going to translate that human-ish language into the zeros and ones that a computer can understand. So our task is now becoming a little bit easier, right? Our task is no longer to speak 0 and 1, speak binary in order to talk to the computer. Now our task is to speak a language that the interpreter can understand in order to convert to zeros and ones. Progress, right? I mean, look, this is getting better already. This is something that we can, as people, can kind of begin to understand. Cool. So that's great. But if you look at it, I mean, this still seems kind of tedious, right? I mean, it looks like it's doing some math, sort of, but there's like 10 lines of code here. There's like a bunch of stuff we have to do. So if we sort of think through what this looks like a little bit, we can kind of be able to try to figure out like, well, what math is it doing? All right, so we get our 3 different things, A, B, and C. These are what are called variables, which we'll talk about in a later module. And it really is about ways for us to identify bits of data. Computers are really bad about keeping track of information and keeping track of different kinds of data that they need to deal with. Effectively, computers have all this stuff stored in memory in their RAM, and they need to be able to track all these pieces. And computers are a little bit like sort of the absent-minded professor in this way, where it's like if you take some data and put it on the desk, then it disappears and they have no idea where it went anymore. So we have to make sure we give labels and names to everything and talk about it. So we tend to refer to things with names like A, B, and C. So in any case, we take our values, our A, B, and C. We're saying that we want to multiply C and 4 and store that variable in temp. So we take C times 4, I'm using a little star to represent multiplication. And then we're subtracting temp from B and storing that inside temp again. But temp, you remember, previously was C times 4. So really that's just another way of saying B minus C times 4. We didn't do the same thing to add that to A, but again, because temp is really just B minus C times 4, that's really saying A plus B minus C times 4, right? So I'm just converting this into mathematics and just sort of expanding these things out, and then saying temp and turning that back into D. So really, in the end, what we did is we wrote, there's 8 lines of code here that really translates to this, really basic arithmetic equation, right? Take A, add it to B, and then subtract the quantity of C and 4, C times 4. Cool. So the question is well, that's really easy. Why don't we just write that? And the answer is that in general, we can. So modern computer programs perform a process what is called abstraction. So this is the process of doing generalization. We're going to be working with this higher level representation rather than all the details. So rather than trying to write down, okay, well, I need to literally take this value and move it over here, and then take this value and add those together, right, in order to create a temporary value in the middle, we can abstract that into sort of a general language of mathematics. We'll be able to say like, okay, great, I'm just going to write down something that looks like a plus b minus c times 4, and I'm going to let sort of that language take care of a lot of the details about like how we store sort of temporary values in order to like add things together. A lot of computer programming is about doing this abstraction. It's about working at this higher level of thinking and sort of higher level of problem solving and letting the computer do a lot of the sort of the details underneath the hood. Abstraction is a lot like trying to drive a car in this respect, right? You're not necessarily thinking about how the engine works or how like the steering wheel is exactly connected to the wheels. You're like, I push on gas and the car goes forward, and that's all you really need to think about. So we're going to try to be aiming at those higher levels so we can think about like, I'm going to write down math and the computer will figure out how to actually add numbers. I don't need to actually explain multiplication to a computer. We can assume the computer knows that stuff. So we can't go totally to just where I say computer, solve algorithm. It's not quite Star Trek level yet, but we can be able to give slightly more generic structures, which will help make it easier for us to explain how we want to solve problems. Great, so we've got this abstraction step that we're trying to go through. In the end, we take this abstraction step, which eventually is getting translated, going through an interpreter, getting translated and translated back down to zeros and ones, and that abstraction we can work in is what turns into our programming language. If we abstract this enough, we get a programming language. So a programming language is going to be a language that a human, like us, is able to write and interpret and understand, but can also be interpreted by a computer. So it's something, effectively, it's like a common ground. It's a place where people are able to understand what's going on, but a computer is also able to understand it enough that a computer can interpret it, can do that massive find replace operation to convert it back into zeros and ones. So computer programming languages are formal languages. They're not natural languages, which means that we have to be really precise and really careful about how we're writing them down. Humans are really good at interpreting language. We're able to speak in vague generalities, and you can talk about all kinds of different things and how these things relate to other things, and these things are then going to do some other stuff, and in the end, you sort of all kind of figure out more or less what somebody's talking about. Because there's context, and there's clues, and there's lots of ways that we can interpret what people are saying. Computers can't do that. Computers are stupid. Computers have no idea what's going on. So computers, you have to be incredibly precise in order to figure out what they're trying to do. So when you want to talk to a computer, you have to be very, very particular about what you say. You can't use vague terms because the computer can't figure it out. And if the computer is just going to be like, nope, I don't get it. It doesn't know what to do. So programming languages are going to be, they're languages in their own respect. They have their own grammar, they have their own syntax, they have their own vocabulary. It's a very limited set because it has to be something that can be understood by a computer. And you can't fake it the way you might be able to do with some other foreign languages you might learn. This is one where you have to be very, very clear about it because otherwise the computer does not know how to figure stuff out. So learning a programming language is really a lot like learning a foreign language. It's going to feel the same. If you've ever learned a foreign language, it's going to be kind of the same way, except that we can't actually, you don't get a lot of the benefits of like, you don't get cognate, you get some cognates. You don't get the same kinds of generality and abstraction sort of and willingness of your listening partner to figure out what you're saying with the computer. So these are these really precise languages. Computers are incredibly literal-minded. They don't have nuance, they don't have inflections, they don't have context, or any of those other wonderful things that language provide. They just understand the literal definitions of what you write. So this process of learning to speak computer, to speak a programming language, to write a computer programming language, is really going to be a lot like learning a foreign language with a teacher who refuses to speak to you in your language, in your native language, and kind of yells at you if you ever get it wrong, and you get things wrong a lot. So yeah, it's not great. There are thousands of computer programming languages that have been written over the last 60 years that computers have sort of been around. New ones are invented every year. In this class, we're going to be working with a programming language called Python, and we'll talk about this more in one of the later modules when we sort of introduce this. This is an example of some Python code, so you can just kind of begin seeing a little bit what this looks like. Again, this is doing more math. I apologize for all the math in my examples. I'm going to try to move away from math later, but this is sort of a good standard example to go with. If you've done a little bit of, like, say, algebra, you might be able to take a look at this and kind of get a sense for maybe what kind of math it might be doing. But yeah, so we're going to be learning in this class. We're learning the Python language in particular. There are lots of programming languages. They're all slightly different, right? They all have slightly different syntax. They have slightly different vocabulary. Some of them are actually fairly far apart from each other, but in general, they're all going to work kind of the same way. So by learning one programming language, you'll actually get a pretty good sense on how the vast majority of these things work. A lot of the concepts are going to be the same. It's similar to how in in natural languages, how like most languages have nouns and verbs and objects and they like tenses, and these things are sort of standard ideas, even if actually what verbs and nouns and tenses you use changes between languages. So the same kind of thing is going to apply to programming languages right here. So we're going to be learning sort of the fundamental way of talking about these languages and speaking these kinds of languages, but we're going to be focusing on a particular kind of language, the Python programming languages. If you need to go learn other languages, it's really just kind of a shift to learning something that's slightly different. It's a little bit like if you know French, you need to go pick up some Spanish, or even if you know learning about how like Americans speak versus how, say, the British speak, right? It's a different, same words, different syntax, different a little bit, right? Different accents, so a couple different vocabulary words and how these things come together. Cool. So we're going to be learning how to write computer code in a language that we can make sense of. We're going to learn how to make sense of that language in a way the computer can understand that. We're also going to be learning how to then manage this code, right? Because writing all these instructions ends up taking up a lot of space and a lot of time. There's a lot of files that go along with this. So a lot of what we'll be doing is going to be a lot of tooling work in order to figure out just how to actually like manage where our code is going and how to keep track of all the stuff that we're doing. So this course is going to be covering both programming, right? That's sort of the main topic, but we're going to have a lot of code management processes that happen along the same way. Cool. So overall, right, our objective for this class is we're going to learn how to give instructions to a computer so that they can go do the boring stuff, right? Our task is to automate it, make it so that computers do the things that are boring so that we can go do the things that are fun and interesting and actually require humans to do some work on. Great. There's one slight hitch to this, however. So we talked about the programming. We have to learn this programming language, right? This language that we can speak to a computer on. But really, computer programming ends up actually involving two separate pieces, right? We need to be able to speak to the computer and tell it what we want to do, but we also need to figure out, well, what are the steps we want to do in the first place, right? What is, not even just like, how do I talk to the machine, but what do I want to say to it? So these different steps that you go through in order to solve a problem is generally referred to as an algorithm, right? That's going to be our process by which we're going to solve a problem. Algorithms are sort of the fundamental concept in computer science. So if you were in the computer science department, that's what you'd study. You'd study algorithms. What are the steps we're going to go through to solve these problems? And then, of course, how do computer programs like effectively do that? Algorithms have their own series of sets of requirements, their own sets of details. In this class, we're going to be doing some algorithm work just by necessity, because if we're trying to figure out how to tell the computer to do something, we have to figure out what are those steps to tell it to do. But the primary focus of this class is going to be on how to speak the language in the first place. I'm going to try to keep the kinds of algorithms, the kinds of steps, instructions we have to do fairly simple. We're not going to go into a lot of detail on the kinds of algorithms you'd use for doing data science or visualization or any of that work, because we're going to focus on mostly how to speak to the computer in the first place. You can cover those kinds of algorithms in other courses. This is an intro course. We're talking about how to speak the language. That said, there's still going to be points where you have to figure out, like, well, not only how to speak the language, how do I use the words that I know to be able to communicate a solution to this problem? So there is going to have to do both those steps, but I want to make sure you're keeping it in your mind that there's two different things you have to worry about. So if you get stuck on the language, it might be like, well, let me put the language aside, let me think about how do I want to solve the problem in the first place? Or if you say, well, I got my solution to the problem, I can get that in place, then I can just think about how to translate it to the language. So there's sort of two different pieces of work you're going to have to sort of approach side by side to make these things happen. All right, finally, I have to make sure to note very carefully, for people who have never done any kind of computer programming before, that computer programming involves a lot of frustration and failure. It's not, I mean, I like it, I think it's pleasant, but there's a lot of pain involved in doing computer programming. The process of computer programming is basically trying to teach mathematics in a foreign language to a petulant 6-year-old. That's what it's going to feel like. It feels like pulling teeth a lot of the time. This is really normal, right? Because computer programming involves failure, and it involves a lot of failure. Nobody writes perfect code the first time. Nobody is able to say, computer, do some work, and have the computer just do that work correctly. It never happens. Never. Right? Never. Does not happen. What you end up doing, though, is you say, computer, do this thing, and the computer does kind of part of it, but then has a problem. So you say, okay, there's a problem, I'll fix that problem and try again. Because it's a computer, it doesn't care, try it again. So you try that again, and there's another problem, and you fix that, and there's another problem, you fix that, another problem, fix that, another problem, fix that, another problem. And then eventually, after a couple hours, right, you finally fixed all the problems, and it works, and it prints out the word banana, and you're like, yes, I've won! And you realize that you're not sure what you've done with your life anymore. But that's okay, right? So again, the process of actually what computer programming really does. It's both speaking the language, but a lot of it's about figuring out how to fix the mistakes you make in the language. So it's not necessarily learning how to speak the language correctly. It's learning how to fix the problems you've made in the language previously, right? It's how do you fix problems that are keeping your programs from working. The process is called debugging, and we'll talk about this more later. So programming is a lot of frustration. It's a lot of failure. It's gonna feel difficult. A lot of what's required to just do programming is really just perseverance. It's a resilience to be able to say, like, yes, that didn't work. That's okay. When something doesn't work, it's really okay. It's normal. Things never work the first time. And when it doesn't work, you say, that's okay. I'm going to see if I can figure out why it's not working, and I'm going to give that a shot and try it again, and maybe that was wrong, and I'll try something else, and I'm going to keep trying and be able to see how it works. This makes it end up being really kind of time intensive, right? Because it takes a lot of time to think about problems. You got to have a lot of failed attempts, a lot of backtracking, a lot of adjustments. It's really hard to judge how long things are going to take. This is part of why we tell you to plan accordingly when you're working on programming. This is a very time-intensive class because this stuff breaks a lot and it fails all the time. So I think I have to note, programming is failure. That's all it is. It's just repeated failure over and over again until eventually it works. But that's not your fault. That's normal. That's like if everything's working the first time, that's not normal. If everything breaks, everything fails, that is normal. That's what we're expecting to happen because that's how the world works. That's how this thing happens. So if you get frustrated, I understand. That's normal. Your stuff fails a lot. That's normal. That's not your fault, and we are here to support you. Our goal is to try to help you through this frustration of figuring out how to speak to this petulant 6-year-old. So my basic guideline, and the way this happens is that if you have problems, if you get frustrated, you get stuck, is to ask for help, right? Come to say, I'm stuck, I don't understand how this is working, seek help, and we are here to help you through that failure and that frustration, because it will occur, and we're there to help. So my general guidelines, just because I want to flag what this is about, so if you get stuck for like 30 minutes or so, that's a good time to ask for help. The thing that I hate the most is when a student comes to me and says, I've spent hours working on this problem. Like, that shouldn't have been hours of your life, right? You don't have that much time in your life. If you get stuck for like 30 minutes, be like, I'm stuck, and I'll help you get unstuck and be able to keep going so you can figure out how to get past that failure. Don't spend hours on this. Spend like a little bit of time on it and then ask. Don't spend no time. Spend a little bit of time, and then you can ask for help. If you feel lost at all, ask for help. Or if you just get frustrated, you just want to like have someone to vent against, or you just need some extra ideas about stuff, ask for help. Don't try to do this in a vacuum. Don't try to do it by yourself. Don't try to just wallow in the failure that will occur, because the failure will occur. But being able to seek out help and be able to sort of deal with that and programming in order to be able to speak to this computer is really what this is all going to be about. Okay, so in the end, remember that we are here to support you. That is what that's the entire purpose of this course. And that's really what the course is about. So like, it's gonna be hard, it's gonna be frustrating, but in the end, you're gonna be able to tell this dude to go like do the stuff that'll make your life easier. And that's gonna be the goal of the class.